Welcome to the practical implementation of data engineering pipeline using Microsoft Fabric. So without wasting time, let's get started. The first thing we need to do is create different workspaces for our data, and we are going to be using NYC taxi data here. So how you can download that, go to nyc.gov.com and select any one of the years. Let's select 2023. I'm going to be using green taxi trip data records and I've already downloaded it. So let's go back to Fabric. Now let's create a few workspaces. We are going to be creating three different workspaces for it. The first one will be source and cleaning. So let's give it source and cleaning. Now go to advanced and let's select the trial version. Click on apply. And in the similar fashion, let's create two more workspaces. New workspace, ML operations, advanced, trial, apply, new workspace. Let's give visualizations, advanced, trial, apply. Now let's move on to the first workspace that will be source and cleaning. And the first thing we are going to do is upload our data file or the Parquet file format that we just downloaded from nyc.gov website. So to upload our data file, what we are going to do is create a new item that will be the lakehouse. So let's click on new item and scroll down inside store data. So this give us the option to store data, organize, query, and store our ingested data in easily retrievable format. And we are going to select lakehouse. So let's select it and we will be giving the name of our lakehouse. Let's give NYC taxi data. So we are going to be uploading our file and then converting into a table format inside our lakehouse. So how we can do that? Our lakehouse is now open. So let's click on get data and upload our file. Let's browse the file. Here it is, green taxi 2023-01, meaning January data. You can download any of the data from nyc.gov website. Let's click on open and upload, and it will take a few seconds. Uploaded. Let's open the files. Here you can see our green trip data is now available, and this is currently in file format, and we are going to be converting this to table. As you can see, currently there are no tables. How we can turn that? So click on the options, load to tables, new table, and we can rename the table. Let's give green data and let's click on load. So this will convert our file into table format for our lakehouse. Then we will be using a notebook similar to Databricks notebook inside our workspace, and we will be performing some cleaning operations on it using Databricks commands, Python Spark commands. So our green data table has now been converted. So we can also expand and also preview our data. Let's wait for it to preview. And here you can see the different columns, vendor ID, L pickup time, drop off time, fare amount, trip amount, everything is and here you can see our data. As you can see, it also has some inconsistencies, some null values and everything. So let's move to back to our workspace and create a new notebook so that we can perform some cleaning operations on it. So how we can do that? Same fashion, click on new item, scroll down, and we will see notebook in develop data. So Microsoft Fabric gave us the option to create and build software applications and data solutions, and we can use Apache Spark notebooks to do that. So let's select our notebook and the first thing we are going to give our notebook a name. So let's give lean data. Let's save. And what we are going to do is select our lakehouse so that we can use that lakehouse data inside this notebook or the lakehouse table. So on the left hand pane, it will automatically give us the explorer. We can add data sources, and you can see we are getting the option lakehouse, and we can also directly upload it, but using a lakehouse is a better option. So let's select the lake house, click on add, and we are going to be selecting the existing lake house without schema, and let's add. And here you can see our NYC taxi data lakehouse is present here in, and the workspace location is source and cleaning. So let's select it, add, and it will give us the table. So what we are going to do, the first thing is copy the URL to our table. So how we can do that? Click on the three dots and let's copy the path. And now let's collapse this. So we will create our DF here. So let's type the command. And this is the command we are going to be using for creating the DF, which is DF equals to Spark, which is the Spark session, read and format. Format is Sparky, and there are we are giving two options. The first one is header equals to true, which means that the first column will be selected as the header or the schema, and the second thing is on infer schema, which automatically means that the Spark will try to guess the schema of our data. And now what we are going to do is connect a new standard session. So click on connect and click on standard session. Even if you don't do that, directly running our cell will change or create the automatic Spark session. Now let's give our URL that we just copied. So let me copy it again. Copy path. Now let's replace the URL. And here you can see our source and cleaning @one lake and microsoftfabric.com, NYC taxi data, lakehouse, and tables, and the name of the table that we just gave. So our session is now started. So let's run our first cell. So this will create a DF and also display our DF. And this will be the same table that we just saw while uploading our data. So let's wait for it. And here you can see our data is present. There are some inconsistencies, some missing values, some null values. So we will be cleaning this data. So let's move on to the next cell. Now let's add a cell. The first cleaning operation we are going to perform is to drop the e-hail fees. As you can see here, let me show you. And e-hail fees, the complete value is null, and you can see the visualization here as well. So it's entirely null. So what we are going to do is drop this column. How we can do that? Now df clean. So this will create a new df from our original df under the name of df cleaned, and then we are going to drop the column that is named ehail fees. So let's run this, and this will also display it. As you can see, there were 20 columns and now there are only 19 columns. So this means that the ehail fees column has now been dropped, and it was next to trip amount, I guess. Yep, tolls amount. And now you can see after tolls amount there is directly improvement surcharge. Now let's move on to the next. And the next thing is we are going to be performing some cleaning operation. So this code is a cleaning data set, and it filters out any rows where the values in certain columns does not meet the specific conditions. So trip distance greater than 0 only means it only keeps the rows where trip distance is greater than 0, meaning it filter out trips with no distance. And fare amount greater than 0, it only keeps those rows where fare amount is greater than 0. Similarly, passenger count greater than 0 only keeps rows where passenger or the number of passenger is greater than 0. Now, and then it will also display that DF. So let's run this. So this will edit our DF in the background and display it under the new name df cleaned, which we previously used for the clean data. And now our data is cleaned with the cells cleaned out. So let's move on to the next. Now in the next cell we are going to be using this will be the code for the next cell. What this is going to do, so this code will be filling in missing values. which are NA or null values in specified columns of the dataset, that is DF cleaned. So congestion surcharge is 0. It means that if there are any missing values in the congestion surcharge column, it replaces them with 0. Tip amount 0. So if there are any missing values in the tip amount column, it replaces them with 0 as well. Now let's run this. So this will clean our data set furthermore. So let's move on to the next step. So now the next step is to rename those columns named EU location to pickup location ID and DO location to drop off location ID and store them in the new DF or the DF cleaned, and this will also display them. Let's run this. So here you can see, let me show you new columns, drop off location ID and pickup location ID. Let me show you the previous ones. It was previously PU location ID and DO location ID. So now it has made us more readable. Now let's move on, and the next step what we are going to do is create a data's deployment pipeline. So go onto the workspaces and select deployment pipelines, and in here create a new pipeline. So let's give any name. Let's just give data deployment and click on next. So here we'll get the option to give the stages or some name. We can give, let's give cleaning. The next one, let's give ML, and the ML, and the final, let's give visualization, and let's click on create and continue. So this will create new 3 different stages. First one, cleaning, the all the operations we have already performed. The next will be ML, so we are going to using the same data that we cleaned and perform ML operations on it. Now the third one will be visualization, so we are going to be creating some visualization after performing the ML operations. So let's click on create and continue. Now we have to assign some workspaces to all these deployment stages. So inside cleaning, we are going to be selecting source and cleaning. Let's select OK. The next is ML. So we are going to be selecting ML operations. OK. The third one, visualization, visualizations. OK. So, OK, let's go back. I accidentally clicked. And here you can see it's currently under progress. Now let's select the cleaning workspace and let's expand this. Here you can see it will show us all the data we have inside our cleaning workspace, all the resources. First one is Lakehouse. So we have SQL Analytics and the NYC Taxi semantic models. Now what we are going to do is use this clean data notebook that we created inside our source and cleaning and copy it to our ML deployment stage. And how we can do that? So let's go to ML, just click on ML and let's select the notebook. So what is this going to do? Create a copy of our notebook that we created inside the cleaning and source and cleaning workspace and make a copy of it in the ML operations. How? Just click on deploy and you can see clean data deploy. So this will create a copy and then we are going to be performing some operations, ML operations on our data inside the ML deployment stage. So here you can see clean data is present inside the ML operation. So what we're going to do, as you can see, compared to source, it's same as source. And we have not selected lakehouse because we do not need it. We can just use the same lakehouse that we created in the first workspace, the source and cleaning workspace, and get the data from there only. So now what we're going to do, open the new notebook that we created and let's rename it. So this is a copy of the clean data. What we are doing is performing the ML operations. So let's give it ML operations notebook, save. Now we do not need to explicitly select our resources, the same path for the first from the first workspace will be available here as well. So what we're going to do is just connect the new standard session and wait for it. Now our session is ready. So what we're going to do is run all of these cells again automatically so that we can perform the ML operations and move forward with it. How we can do that? Just click on this run cell arrow and select run this cell and all below. It will take a few seconds and then run all of these cells that we already ran in the new notebook that we have copied, and then we are going to be performing some ML operations on it. So let's wait for it to run properly. And this is the first code snippet for our ML operations. So let's also add a small markdown and let's write here ML operations. So just a distinguishing factor. Now let me explain. So what this code snippet does is it uses PySpark to prepare data for machine learning, especially for scaling features and transforming the data into the appropriate format for training a machine learning model. So let us break it down. The first thing, imports. So the first import is vector assembler. So this is a feature transformer that combines multiple input columns into a single column vector. This is required because machine learning algorithms in Spark expect a column of various vectors as input. The second one, standard scaler. This is used to scale the features and standardize them. It scales the feature vectors to have zero mean and unit variance, which is a common processing step in many machine learning algorithms. The third thing is pipeline. So this is used to chain multiple stages such as transformers and estimators together into a single workflow. It allows for a clean and organized way to apply transformations and modeling steps. And then column, this is simple. This is a helper function from PySpark's SQL, and that is used to refer data frame columns. Now, what we are doing is setting up the columns. So the feature columns, so these are the columns from the data frame that will be used as features or predictors for this model. In this case, they relate to trip details like distance, number of passengers, rate code, surcharge, and trip. And then target columns. So this is the column that you want to predict or the dependent variable. Here the target is fare amount, which is likely the amount of money the taxi fare costs. The next thing is vector assembler. So vector assembler takes multiple columns specified in input columns like feature vector columns and combines them into a single column of feature vectors. The output is stored in a new column called features assembled, and this step is important because Spark ML libraries models expect features to be in vector form. The next is standard scaler. So the standard scaler takes the assembled features from the features assembled column that we created and then standardizes them by scaling each feature to have a mean of 0 and standard deviation of 1. This is done to make sure that the features are on a same scale, which can improve the performance of many machine learning algorithms like regression, clustering, SVM. Then pipeline. So this creates a pipeline that will first apply vector assembler and then apply the standard scaler. Each step or stage in the pipeline is executed sequentially. The pipeline makes it easy to manage multiple transformations and model fitting steps in a single unit. And pipeline.fit df cleaned. So what this is going to do is this fits the pipeline to the df clean data frame, meaning it learns any necessary statistics for transformations like computing the mean and standard deviation for scaling. And then transform df cleaned. This applies the transformations like vector assembler and standard scaler to the clean data frame, resulting in a new data frame where the features are assembled into a vector and scaled. Now what the final is selecting the final columns. So this step selects the features scaled column, the scaled feature vectors, and renames the target column fare amount to label. In machine learning, the term label is commonly used to refer to the target variables. So let's run this. This will take a few seconds to run. Let's wait for it. This is just the data preparation for ML, and the output will not be anything. And we are going to performing some operations after this, and then we will get the output of our data. So let's wait for it to run, and then we will perform some ML operations on our data. And our ML data preparation is now done. So it just gives us the run name and how long it took, 34 seconds. And in the experiment name, it just gives the notebook name. So this is the new run name that was automatically generated. The next thing what we are going to do is perform splitting our data. So what this code does is it splits the prepared data frame into two subsets, one for training and one for testing. So let's break it down. The random split. This method is used to randomly split a data frame into multiple subsets. In this case, it's used to split prepared data into two parts, a training set and testing set. So point 8 and point 2. This argument specifies the proportions in which you want to split the data. Here, point 8 means 80% of the data will be used for training or trained data, and point 2 means 20% will be used for testing or the test data. Here we have defined the train data and test data, and point 0.8 for train data and point 0.2 for test data. And seed equals to 42. This sets the random seed for the split, ensuring reproducibility. In other words, every time you run the code with the same seed, you will get the same train or test split. This is useful for consistency, especially when you are comparing models or result across different runs. Now, train data and test data. These are two data frames that result from the split. After executing this line, you will have train data, a subset containing 80% of the data, which will be used to train your machine learning model, and test data, a subset containing 20% of the data, which will be used to evaluate the performance of the model after it is trained. So, why split the data? So, training set, this subset is used to train the machine learning model. The model learns from this data and adjusts its internal parameters accordingly. And test set, this subset is kept aside and is used to evaluate how well the model performs on unseen data. Using a separate test set helps prevent overfitting as the model is tested on data it hasn't been trained on. So let's run this. And now let's move on to the next. And the next code snippet is this. So what this does is this code is using PySpark to train a linear regression model on the trained data and then evaluates its performance on the test data. These are the two data frames we created in the previous command. So let's us understand. Let's first start with the imports. The first import is linear regression. This is the model for linear regression in Spark's ML library. It performs regression tasks by fitting a linear model to the data. The second one is regression evaluator. This is used to evaluate the performance of regression models. It computes metrics like root mean square error or RMSE, R squared, and others based on the predictions or the true values. The next thing we are going to do is creating the linear regression model. So using LR equals to linear regression, what we are going to do is we are initializing a linear regression model, and features column equals to feature scaled. This means that this specifies that the input features for the model will come from the column that is called feature scaled. These are the scaled features which were processed earlier. And then label column, this specifies that the target variable or the values you are trying to predict will come from the column named label, which in this case corresponds to fair amount. Then what we are doing is fitting the model. So fit train data. This steps trains the linear regression model that is named LR in the previous step on the train data. The model learns the relationship between the features feature scaled and the target that is labeled using the training dataset. And after calling fit a trained model LR underscore model dataset, this is returned. Now, after this, we are making some predictions. So using transform test data, the trained model or the LR model is now applied to the test data to make predictions. This step generates predictions based on the features of the test data. And then the transform method adds a new column called predictions to the test data frame, which contains the model's predicted values for the target variable. Then what we are doing is evaluating the model. So, okay, standard session. Don't worry, the session is run out. What we can do is view the session information, expires in, let's make it to 60 minutes and let's apply. And then what we are going to do is run all the above commands so that we can store the data. So after a session has been deleted or expired, what it does is removes all the functions we have performed. So let's run all of these cells below and let's continue with the explanation of our current what we are going to do. So we were at the step of evaluating the model. So this evaluator, what this is doing is this object is used to evaluate the performance of the regression model. And inside here, label column equals to label. This specifies that the actual values or the true target values are in the label column. And then prediction column, this specifies that the predicted values are in the prediction column. And then metric name RMSE. This indicates that the evaluation metric will be RMSE or root mean squared error, which measures the average magnitude of the errors between predicted and actual values. Lower the RMSE values indicate the better model performance. Then evaluate. This evaluate predictions. This method computes the RMSE model for the model's predictions on the test data, predictions data frame. And then the result is stored in the RMSE variable. And this is just printing the root mean squared error and the output of the RMSE variable. Now this display is pretty simple. It's just displaying the predictions, and this selects the columns that are named predictions and labels from the predictions data frame. These columns show the predicted and the actual target values for each row in the test data. And then the display function is used in notebooks to display the results in tabular format. So in summary, what this is doing is creating a linear regression model. So we are training a linear regression model that is under the variable LR and using the scaled features under the variable name features underscore scaled and the target variable under the variable label, and then making predictions. The trained model then makes predictions on the test data, and then we are performing the RMSE evaluation. This is the root mean squared error, which generates the average error between predicted and actual values. And then we are displaying the predictions. And we are displaying the predicted values alongside the true values for easier comparison. So let's take a look at the output. And here you can see it's just the run name and then it has created the prediction and the label comparison. Now let's move on to the next cell. Here you can see it has also displayed the root mean squared error value and it comes out to be around 10.48. Now in the next cell, and the next thing we are going to be performing is the Pearson correlation. So this Pearson correlation coefficient calculates the correlation between two columns, that is trip distance and fare amount, from the df underscore clean data frame. The Pearson correlation coefficient is a measure of the linear relationship between two variables where a value close to 1 means a strong positive linear relationship and a value close to -1 means a strong negative linear correlationship and a value close to 0 means no linear relationship. So let's break down it step by step. So we are importing CORR or core It is a function from PySpark SQL functions that computes the Pearson correlation between two columns in a data frame. And then we are calculating the correlation. So select correlation. We are calculating the correlation between trip distance and fare amount and aliasing it as correlation. And then, so this renames the result to correlation and collect what this does. Let me select it. Collect what this does is it is used to retrieve the result of the correlation computation as a list of rows. The collect method is necessary because PySpark operates on a distributed data and calling .collect brings the result back to the local driver or the machine running your PySpark code. This result will be a list with a single row containing correlation value and 0 two zeros in square brackets. What this does is after calling the dot collect, the result is a list with one element, a row object, to access the correlation value. And we are using 0 0 to extract only the first and only element in the list and then the first and only value in that row, which is the correlation coefficient. And then we are going to be printing the correlation coefficient. So let's run this. Here you can see the correlation coefficient comes out to be around 0.3. So a positive correlation coefficient means that the trip distance increases, the fare amount tends to increase as well. Now let's move on to the next. And the next thing we are going to do is calculate the T statistics for comparing the average fare amounts between the two groups, that is payment type 1 and payment type 2. So let's understand what this is doing. First thing is data grouping. So it groups the data by payment type, either 1 or 2, and calculates statistics like mean fare, standard deviation under the name of std_dev underscore fare, and count under the name of count and of the fare amount of each group. And then it extracts the group statistics and which is used to calculate the statistics like mean, standard deviation, and count for both the payment type 1 and payment type 2. And then we are going to be performing the t-test calculation using the mean 1 and mean 2 for the fare amounts of each group, and standard deviation 1 and standard deviation 2 for the standard deviation of the fare amounts of each group under the total number of records n1 and n2. Now let's run this. This will give us the value of the t-tests calculation. Here you can see the t statistics between the payment 1 and payment 2 type is 2.818. Now let's move on to the next cell. So let me also explain what the value of the t-test statistics signify. So the t-test statistics value of 2.18 signifies and indicates the magnitude of difference between the means of the two groups that were payment type 1 and payment type 2 in terms of the variation or standard error in each group. To interpret this value, let us understand. So a higher absolute t statistic value, usually greater than 2, suggests a significant difference between the two groups, meaning the fare amount for the two payment types are likely to differ in a meaningful way. A lower t statistic value, which is closer to 0, would suggest that the difference between the two groups mean is small and relative to the variability within each group, implying that any observed difference might be due to random chance. For a t statistic of 2.185, depending on our significance level, which was 0.05, we would typically reject the null hypothesis, which assumes no difference between two groups, and conclude that there is likely a significant difference between the average fare amounts of the payment types 1 and 2. Now let's move on to the next step. The next thing what we are going to do is perform some visualizations, and to do so we are going to be moving to forward with our third workspace. Now let's go to our data deployment pipeline, and in here we are going to be selecting the third visualization, and we are going to be copying or deploying the notebook that we created in second one. the ML operations notebook and deploy it to our third stage of the visualization. Now let's click on deploy. So this will create a copy of ML operations notebook to our third workspace. And then we are going to be performing some visualizations on our cleaned and operated data. And our deployment was successful. So let's open our notebook and let's rename it as well. Let's give visualizations notebook. Let's save it. And we do not need to connect our lakehouse or anything else. What we just need to do is connect a new standard session. And then we are going to run all of our code blocks that we ran before to get our data to the optimal level that we just used. And then we are going to be creating some visualizations. So let's wait for the standard session, and session has started. Let's run all of these cells and it will take a few minutes. So let's wait for it. Now all of our cells have run successfully. So let's start with the visualization. So let's move to the end and let's create a markdown cell to display visualization. And let me get the code for the first visualization. And this is the code for our first visualization. So what this code does is it is visualizing how well the predicted fair amounts match the actual fair amounts. So a simple breakdown. Convert to pandas data frame. So it converts the Spark data frame predictions into a pandas data frame under the name of pandas underscore df, which contains three columns: feature scaled, label or the actual fare, and prediction or the predicted fare. And then we are plotting a graph. So the code creates a scatter plot where x-axis shows the actual amount or the actual fare amounts under the name label, and y-axis shows the predicted fare amounts under the name predictions. And each point represents a pair of the actual versus predicted fare amounts. Now let's run this. The plot also has a title and label for the axis, and the grid is enabled for better readability. So the closer the points are to a straight diagonal line where predicted equals to actual, better the predictions are. If the points are scattered far from this line, it indicates the larger prediction errors. So let's take a look at this graph. Here you can see if the points are closer to the 45-degree line, it means that prediction is good, and if they are far off, it means that our prediction were wrong. Now let's move on to the next cell or the next visualization. And now our next visualization is the correlation matrix. So this code is used to calculate and visualize the correlation between different numeric columns in a data frame. So let's break it down. The first thing is handling the n values. The select function loops through all columns in df clean data frame and replaces any values that are n or none or missing values. So this is done for each column. And then we are identifying the numeric columns. So the numeric columns list is created by checking the data type of each column. Only the columns with the data types starting with int or double are selected, and then we are creating a correlation matrix. The numeric columns are extracted and converted to a pandas data frame, and then the CORR or the correlation function is applied to calculate the correlation matrix, which shows how each pair of numeric columns is related. A correlation value close to 1 means a strong positive correlation, while close to -1 means a strong negative correlation, and 0 means no relationship. And then we are putting it all in a heat map. So a heat map is created to display the correlation matrix. Each cell will show the correlation value between two columns. And the color scheme we have decided is cool warm to help quickly spot strong positive or negative correlations. The ANET equals to true. This adds the numeric correlation values to the heat map. Let's run this. So in summary, this code cleans the data by replacing the null values. Let's Let me check if there is an error right now. Oh, the error was because SNS was not imported. So let's import Seaborn as SNS. And now let's run this. So this will create a correlation matrix. And here you can see the result. Let me zoom out so that you can see properly. Now let's move on to the next visualization. And now the next visualization is a histogram. So this code will create a histogram to visualize the distribution of the label column, which likely contains the fare amounts and from the pandas DF data frame. So sns.histplot. So it creates a histogram of the label column, and KDE equals to true adds a smooth curve, or KDE is kernel density estimate over the histogram. Then bins equals to 30 sets the number of bars or bins in the histogram to 30, and color equals to blue makes the bars blue. And then we are giving the title distribution of actual fare amount, and we are labeling the x-axis as fare amount and y-axis as frequency, and frequency represents how many times a fare amount appears, and then we are displaying the histogram. So let's run this. Here you can see. Now let's move on to the next visualization. And the next visualization we are creating is a bar plot. So this code calculates the average fare amount for each payment type and creates a bar plot to visualize the result. And it groups the data by the payment type column and calculates the mean fare amount for each payment type, and then converts the result into a pandas data frame using the two pandas, and then renames the columns of the data frame for clarity as payment type and average fare. And then it creates a bar plot, sets the size of the plot as 8 by 6, and plots the bar chart with payment type on the x-axis and average fare on the y-axis, and variates the color palette is used for the bars. Now let's run this to display our bar chart. Here you can see the bar chart. Now let's move on to the next visualization. And the next visualization is fare amount by trip distance range. So it's pretty simple visualization. So let's run this. Here you can see trip for 2 to 5 miles and the fare amount, 5 to 10 miles and the fare amount, and greater than 10 and less than 2 miles and the fare amount. Now the next are the few optional visualizations. So let's run these as well. And the final one will be the correlation matrix in a different format. This one is predicted versus actual fare amount to test our hypothesis and our ML. So let's wait for it to be visualized. And here you can see it's the similar graph that we created upwards, but it is a little bit interactive so that we can see every dot value predicted and actual amount also here as well. Now the final is correlation, but a little different, a little bit interactive. That's all for this data factory data engineering pipeline. Thank you so much.